This video is to try and support you if you were struggling with the marking and improving of the homework for part 2 of Forces Out a speed time graph, a velocity time graph. So there are some things to recall about speed time graphs, and that is that the gradient will show you the acceleration or deceleration, and the area underneath the graph will show you the distance travelled. This is a graph that's talking about stopping distances as well. So it's saying that the driver's seen this rabbit at the start of the graph, and then the driver makes an emergency stop to avoid hitting the poor cute little bunny rabbit. So this graph is showing us both the thinking distance and then the braking distance from the point of seeing the rabbit to the car stopping. So this first bit of the graph here to here, this section there, is all the thinking distance. The driver has seen the rabbit, they're reacting to seeing it, and they're putting their foot on the brake, but they're continuing to travel at 16 metres per second for that half a second that it takes them to see the rabbit and then put their foot on the brake. The rest of this graph here, or this area, and this sloping gradient here where the speed is decreasing in time, it's decelerating, is when the brakes are being applied and the car is coming to a stop by the 2.5 seconds of time after the driver has seen the rabbit. So that was quite a long explanation of the graph, but if you're watching this video it's because you were stuck on this question, so you might want a little bit extra help. So the distance that's travelled by the car from when the driver first sees the rabbit to when the car starts to slow down, that is the reaction time of 0.5 seconds. It's the first part of this graph because that is the distance that's travelled while the driver thinks about putting their foot on the brake. So that correct answer has to be D. The first part of that graph is showing the thinking distance during the thinking time. To calculate that distance, if you're going for the pure core knowledge area under the graph, then you have got a rectangle shape here that's 16 high by 0.5 across. So you do 16 times 0.5, which gives you 8 metres. Another way to think about that though, say you've forgotten the core knowledge that you need the area under the graph to show you the distance, you can just think it's going 16 metres every second, and it's travelling for half a second. So if it goes 16 metres in a whole second, in only half of that second, 16 divided by 2 gives us 8 metres in 0.5 seconds. So you could do it either way, as long as you show you're working out clearly to make sure you get all 3 of those marks. If we think about the definition of acceleration, acceleration is the change of velocity in time. So it's the change of velocity, v minus u, divided by the time taken. Final velocity take away initial velocity divided by the total time taken to change velocity. So looking at our options, A has to be the correct answer. I really should check the mark schemes before I make these videos. I hope that's right. I'm sure that's right. I'm doubting myself now. Right. So then we have to calculate the deceleration of the car. So we're going to have a minus acceleration answer because it's a deceleration. So the acceleration can be calculated from the final velocity. Well, the final velocity is here, 0 metres per second. Take away the initial velocity, which is here, which was 16 metres per second. And we need to divide that by the time. Now, the time it took to change that acceleration is 2.5 take away 0.5. This distance on the x-axis is worth 2 seconds. So we divide that by 2. So we've got acceleration equal to minus 16 divided by 2. The acceleration therefore is minus 8 metres per second squared. But it's a deceleration, so we don't have to put that minus because that's what it's telling us. The minus is telling us it's decelerating. The deceleration has a value of 8 metres per second squared. I hope that helped if you were stuck on the question. So in this calculation question, you're told you've got to select an equation from the list. So this is an apply only, not a learn and apply equation. So we can immediately, before even thinking about the question, jump to the formula sheet and remind ourselves there's only two equations that we're choosing from for topic 2. The only two equations that it could be are v squared minus u squared equals 2ax, or the other version of Newton's second law, the change of momentum divided by time is the force. So it's one of these two equations. So as I then read through the question, I'm going to work out which bits I know. So the car has a mass, I know m, so I know that in that equation, and there's no m in the first equation, at a constant velocity, so that could be v or u at the moment. The time taken is what I need to find. Now that's really important because this equation doesn't have time in it, and this equation does. So it's going to be the second equation, I think, don't you? We're then told a force. So I know the force for this equation. There is no force in that first equation again. So it's, before I've even finished reading the question, I know which equation I'm going to be choosing. What I have got to work out is, do I know v and do I know u? Because then t will be the only thing I don't know. So it's going to accelerate the car to a new velocity, a final velocity of 30. So this is my v, which means 5 meters per second has to be u. So yeah, I know everything that I need to do this equation, and I've got to make sure at the end I don't drop 1 mark for not following that instruction about 2 significant figures. So substituting in everything I know, the force, 4,500 newtons, all in standard units in the question, so I haven't got to convert any, is 3,000 kilograms times by the final velocity, 30. And I've got to take that away from the same mass times by the initial velocity, which was only 5, because it's speeded up, it's accelerated, so the final velocity is higher than the initial velocity, and that's all going to be divided by time. So now I'm going to use my calculator and work out 3,000 times 30, which is 90,000, and 3,000 times 5, which is what worked out for me. And then I'm going to build in another step. I really am doing this step by step. So when I do 90,000 take away the 15,000, I'm left with 75,000 divided by t. And then if I times both sides by t, they cancel out here. And then if I divide both sides by 4,500, they cancel out there, leaving me that t will be 75,000 divided by 4,500, which comes to 16.6 seconds. Now, if you didn't like that bit here, if you didn't like the way that I used the balance method to rearrange the equation, you have got another option at that stage. If we just do that over here, it will still get us to this same answer. But we were at the stage where we knew that 4,500 was equal to 75,000 divided by t. So I could have made a triangle at that stage, and the triangle would have had the 75,000 here, the t down here. Have I just put an extra 0 on that? I have. And 4,500 here. So if I cover over t, it's showing me that this is the working out I need to show from using my triangle to make sure I get the point. And it's exactly the same because we get to the same answer. But for that last mark, I must follow the instruction to 2 significant figures, so I need to round up to 17 seconds. So I'm going to show you how I would tackle the planning of this 6 marker by reading it completely blank now. Like, I haven't read it before, I've just copied it in and put it on the screen, so you can see the way that I would think through preparing to answer the 6 marker question. So as I start reading the question, because that's what I've got to do first, read the question through, I'm also going to start thinking as I read it. So a car is moving at a constant velocity. That is important, that bit of information. And it's moving towards a brick wall. So I'm building a picture in my mind right now of this car and a brick wall. And the car is moving towards the brick wall. Doesn't look like it's going to end well. The car collides head on with the brick wall, right? So the car's going to crash into the wall. So it was moving at a constant velocity, and then it crashes into the wall, and then it will stop moving. The velocity will become 0 meters per second because it will collide into the wall and stop. I've got to use Newton's laws. Now Newton has 3 laws, 1, 2 and 3, so I might want to build those in. I've got to explain the forces that are acting on the car before and after, and during the collision. So before and during. So I'm already thinking that's going to split into 2 lots of 3, really, 2 paragraphs. I'm going to have a paragraph about the forces before and a paragraph about the forces during. Okay, so reading through the question, I've built up a picture in my mind of what's going on. I'm now going to try thinking through what information I've got and how to link in Newton's laws. So Newton's 3 laws. 1, balanced forces cause no change, the law of inertia. So if forces are balanced, nothing will change, and that's what's happening at the start here, is it's at a constant velocity. So that means at the start there is no resultant force, or the resultant force is 0. There is no acceleration because everything's staying the same. There's no change in any of the motion, no change at all. It's obeying Newton's first law of motion. There are balanced forces, and those forces will be, for that car, you've got a thrust force that's forwards, and it's being perfectly balanced by all the frictional forces that are acting in the opposite motion, the opposite direction to the motion, and that would be friction between the rubbing surfaces and things like air resistance as well. So the total of those frictional forces is going to be equal to the total thrust from the engine, because there is no resultant force to make a change to the velocity. The velocity is constant because the forces are balanced. There is no acceleration, which you could link to law 2, F equals ma. There is no acceleration because there is no resultant force. That equals 0. When the car collides with the wall, there's going to be a very rapid change in acceleration. Okay, that's going to happen over a time of the collision. There is going to be a deceleration, and it's going to be a rapid one when it hits the wall. Therefore, the forces cannot be balanced. It must be unbalanced, because there has to be a resultant force to cause that change. The resultant force here on this mass of the car is causing a rapid deceleration here. And we can also think of Newton's second law in terms of momentum, which we've just practiced actually in the question just before, in the part before, that during the time of that collision, this resultant force that's acting is going to change the momentum from having momentum to 0, because, other way around, ending up with no momentum from having momentum at the start, because the car was moving at this constant velocity and then it will stop moving. So there's a change of momentum. The change of velocity on that mass over time is because of the resultant force, and that resultant force comes from the wall. So when the car crashes into the wall, there's a force of the car on the wall, but there is an equal and opposite force, and that's where Newton's third law comes in. Every action has an equal and opposite reaction. So there is an equal and opposite force from the wall pushing back onto the car, and it's that resultant force that will rapidly decelerate the car, changing from having momentum to not having momentum over time. And then the car will squash, it will change shape, it will deform the car in that collision because of those forces. I think I'm ready to write my answer.